Welcome to Pomodoro Joe for Saturday, April 1st, 2023. Today we're doing LeetCode problem 704, binary search. This is an easy problem. All right, so given an array of integers, nums, which is sorted in ascending order, and an integer target, write a function to search for target in nums. If target exists, then return its index, otherwise return -1. You must write an algorithm in O log n runtime complexity. All right, there's a lot to unpack in this. If you're new to programming or if you're new to binary search, I'll try to explain it all. If you are an old hand at all this, you can probably skip this whole video. Don't worry about it. All right, so first thing we'll talk about is what is binary search. So binary means essentially two. You have two choices. So the bi in the binary search means two. It's like a biplane has two sets of wings. A bicycle has two sets of tires. Binoculars have two sets of oculars. Noculars? Anyway, so with the binary search, you will be taking your search area. That's this nums. So you take that search area and you divide it into two. So you have a low half and a high half, or a left and a right, whatever you want to call it, but you divide it into two pieces. Now, once you have your two pieces, you can figure out which side that target is going to be in. And once we've figured out which half to look in, we do the same thing again. We take that upper half, that becomes our new search area, we divide it into two, look at that upper and lower half, and keep going until we find our target. Okay, so I will show you the recursive algorithm, but it's confusing and slow, but I'll show it to you. So, before I get started, let's explain this thing here. You must write an algorithm with O log n runtime complexity. What does that mean? So big O notation is a way of just generally getting an idea of how well an algorithm will perform. So the n in the big O of n notation stands for the magnitude of the input. So in this case, n would be how many numbers are in our nums. When you say O of n, that's just saying you can go through every single number and the runtime complexity will scale linearly with how many numbers are in your nums. Now, O log of n means that you have to divide the problem in half every step along the way. So your complexity will be the logarithm of n. It's a little bit confusing, I know, especially if you're new to this kind of thing. It's not going to make a lot of sense. It'll take some practice, and through experience, I think you'll start to understand this a little bit better. Okay, so with that, we will put 25 minutes on the Pomodoro timer and get started. So the first solution I will show you here will be the recursive solution. Now this one will be a little bit more confusing, probably. It'll also be a little bit slower, so this is not necessarily the best way to solve this problem, but I hope it will illustrate a little bit about how to solve this problem, how to approach this problem, and how recursion works. After we do the recursive solution, then we'll jump in and we'll do an iterative solution, which will be a little bit cleaner, a little bit faster, a little bit better. Okay, so recursion just means that we will be calling the function itself from within the function. Okay, that's confusing. So recursion, blah, blah, blah. Okay, at this point, I was even boring myself. I am not going to subject you to this because it was so boring. But I did write a recursive algorithm. I'll leave a link in the description. You can check it out. It's on my GitHub. But the recursive algorithm is slow, and you don't even want to use it anyway. Check out the iterative solutions. Are slower than iterative solutions. All right, so it passes all the tests, and we do okay. We beat 51% for runtime, 59% for memory, 58% for memory. Okay, that's not too bad. But let's jump back here, and let's do this whole thing again, but let's do this iteratively. All right, I'm re-recording this whole thing because I was totally boring myself with that last one, but I promised you the iterative solution, so here it is. So with the iterative solution, it's very similar to the recursive solution. The only difference is instead of calling the function itself, we're just going to keep track of our indices. So we'll have a low and a high index. So our low index will be equal to 0, and our high index will be equal to the highest index in our nums. So that's the length of our nums minus 1. Now we have our loop. So instead of doing a recursive call, we'll be doing a loop, and we'll just say while our low is less than or equal to our high. Actually, I just think we just need to check if it's less than or high. So while the low is less than the high, we'll get our midpoint. And now the midpoint is going to be not just the midpoint of the entire nums, it's going to be the midpoint of our current range, which is between low and high. So we need to say low plus, it's a little bit of math here. So this is going to be high minus our low. Now in this case, we're saying high minus low because that's going to give us the number of elements in our current range. Divide the whole thing with an integer divide by 2 to give us the midpoint between high and low. And then we need to add in our low as the base, just as we did with the recursive solution. All right, now we check our midpoint. If the target is, let's see, no, I'm going to say if the midpoint is less than the target. I think that's easier. So if the num at our midpoint is less than our target, that means we know the target has to be between the midpoint and the high range. So we can adjust our low up to our midpoint plus 1. We know it's not at the midpoint because the target is greater than the midpoint. Otherwise, we know that the target has to be somewhere between 0 and our midpoint. So we adjust our high down to our midpoint. Now at this point, we should have converged on our target by the end of this while loop, and we can just return our result. Now, if the result doesn't contain the target, or if our nums doesn't contain the target, then we do need to return -1. So we'll return -1 if the nums at our low does not equal the target. So that means we've converged on where the target should be. If it's not there, then we return -1. Otherwise, we'll just return low because that is the index of our target. All right, that should be nums. Let's do this. And we passed. Now let's see if we can beat our recursive algorithm. And we do. Now we're beating 64% for runtime and 58% for memory. So that is a significant improvement. Actually, it's not. It's only a little bit of an improvement. From a 51% to a 64%. We do okay. Are there things that we can do in here to make it a little bit better? There probably are. One thing we can do, so this math, if you actually worked it out, so you could say, if you wanted to, this is low plus, let's see, this high minus low divided by 2. You could break this whole thing out and say, let's see, let's split these up. So that's high divided by 2 minus low divided by 2. So we get the same denominator. Now let's get the same denominator on this guy. So we can say this is 2 times low divided by 2. That's essentially the same thing. So that actually becomes low divided by 2 plus low divided by 2 because we've got 2 of them. So this is low divided by 2 plus low divided by 2. So our 2 low divided by 2 plus high divided by 2 minus low divided by 2. All right, so that means that this low divided by 2 and this negative low divided by 2 can be canceled out, just like that. And this whole thing looks like it's low divided by 2 plus high divided by 2, which is the same as just low plus high divided by 2. Whew. All of that to say is we could do this. Low, low plus high divided by 2. It's the same thing. That might save us just a little bit of runtime here. All right, what else can we do? There's not a whole lot we can do here. We could change some of our function names, I guess, or variable names. Okay, that gives us a little bit of a boost. Now we're beating 72% for runtime and 13% for memory. The only thing left here is maybe change some of these, maybe change the order of comparison, maybe change some of these names. It's not really worth it. At this point, we are doing a binary search. We're running an O log n time. We have a decent algorithm. It's clean. It's easy to read. It's easy to understand. I'd say we're done. All right. Well, with that, I am finished. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.